Hello and welcome to the web series ZeroPM Pieces. In the ZeroPM Pieces, the researchers in the project will tell you about one piece of the ZeroPM puzzle that they're working on. So without further ado, here comes a ZeroPM piece.
Thanks a lot, Hans-Peter. So I will start with this pieces presentation about ZeroPM approaches for water treatment, where we today will discuss or present something about our recent research regarding the electrochemical degradation processes. So it's Heico, Schell, my colleague, and me who were working on this during the last years. And just let's start with a little introduction on where we are from. So as Hans-Peter said, we are from TZW, or the German Water Center, in Karlsruhe, South Germany. Our institution belongs to the DVGW, or the German Technical and Scientific Association for Gas and Water. And in different departments of the TZW, where we are around about 200 employees, we are implementing anything regarding the research on water topics, so groundwater topics, drinking water topics, and so on. So we're quite an interdisciplinary team. And Heico and I are especially from the department Water Microbiology, the section Environmental Biotechnology and Molecular Biology. So I am a microbiologist, and Heico is more the chemist in our department, and that's quite nice to work together there. Mostly we are, our research topics, regarding the contamination concepts at contaminated sites, or new degradation pathways, where we also joined the ZeroPM project in. Here are, just to introduce the topic a little bit, but I think you're all quite familiar with the frame of this presentation. Here are listed the treatment options for PFAS in water. So as you all know, we can eliminate PFAS from water by adsorption, flocculation, liquid-liquid separation, or destruction. And today we want to discuss about electrochemical degradation, which is a destruction approach, one of the almost only ones up to for today's research status, I would say. And we also talk a little bit about activated carbon and ion exchange in connection with the electrochemical degradation process. The objective within ZeroPM, within the work package 7 for us, was the development and optimization of a combination of techniques to remove PFAS from groundwater and drinking water. And I think maybe this slide here you have already seen several times. The principle or the idea within ZeroPM was to first apply activated carbon to remove the long chain PFAS, then add a step of ion exchange to remove also short chain PFAS to produce clean drinking water, and then regenerate this ion exchanger with a specific regeneration solution to create a PFAS concentrate, which can then be optimally destroyed, or the PFAS in this concentrate can be destroyed by electrochemical degradation. And so this was our approach to test this, if this is possible. Another option to produce a piece of PFAS concentrate would be to desorb PFAS from activated carbon. And this is possible by polarization of the activated carbon. So our idea here was to put an anodic polarization on granular activated carbon. We have such columns here in the lab where we study this to enhance the absorption of also short chain PFAS here, and then to turn around the polarization to induce or to stimulate the desorption of these PFAS again, to also produce a concentrate which can then be subsequently again be destroyed in electrochemical oxidation processes. So this is the two processes to produce PFAS concentrates, which then of course have to be treated further. And I just wanted to shortly show you that it really works. In our lab experiments, we tested it, for example, with TFA and also PFBA, so two very ultra short chain PFAS. And what you can see here is the effluent of this activated carbon column, where the column against the control or the non-polarized column for these two substances. And you can see that if we put anodic polarization on, then the TFA concentration in the effluent is definitely lower compared to the control column. And when we change the polarization to cathodic, then we have an immediate desorption of high TFA concentrations in the effluent. So this principle really works, and we can generate a PFAS concentrate by this method. And it's for these both substances which are shown here, but this is just exemplary. We have also shown it for other substances. And now we come to the treatment of the PFAS concentrate from either ion exchange or activated carbon. And for the electrochemical oxidation experiments, we have two scales in the lab. The one is here, what you can see, a little 1 liter electrolysis cell, and the other one is a big plant by the company Condias, which can treat 20 liter of concentrate. And yeah, we performed different experiments with different matrices and different PFAS mixtures, or also single substances here. And I just shortly want to tell you about the principle of the electrochemical PFAS destruction. This is the plant again, and here you can see the zoom in on this electrode package. So we can fill our PFAS solution here, and then it's pumped in circularly through this plant. And always when the solution comes in contact with this electrode, the oxidation reaction can happen. And you can also vary the conditions of this plant by pumping slower or faster to increase or reduce the contact time also with this electrode package here. And in principle, we have two pathways that can lead to PFAS destruction or oxidation. On the one hand, we can produce, or it can hydroxyl radicals can be produced at this diamond anode, which can then lead to a PFAS destruction, in the best case to a complete mineralization to fluoride and carbon dioxide. And on the other hand, it's also possible that the PFAS react directly at the diamond electrode and be transformed to shorter chain PFAS, and also here again, in the best case, further to only free fluoride and carbon dioxide. Of course, as we never have ion-free water, there are also side reactions that can happen here. So chloride or bromide, which is in the water, can also be oxidized here, and we can have some byproducts which we would like to avoid. So we were testing different conditions for the electrochemical PFAS elimination. We took a look at the different matrices, at the water hardnesses, so the electric conductivity influence. We tested several pump rates and also several currents. And the first result, which I want to show you, is the regenerate from the ion exchange. I told you before that this was the PhD of Lukas Lesmeister, that they used a sodium hydroxide solution at very high molar concentrations to regenerate this ion exchanger. And they gave this regenerate to us, and we tried in a very small scale, first of all, to destroy the PFAS. And as you could see, even after 300 minutes, no destruction or reduction of these PFAS occurred. Then we scaled this up and tested it with the big electrolysis plant at different pump rates as well. And also here we could not see any effect. And the first thought was that it's possibly because of this very high electric conductivity of the regenerate solution, which was at 150 millisiemens per centimeter. And therefore we tested the same with an artificial solution with a very much diluted sodium hydroxide solution. And there we could see that it worked now. So the electric conductivity of the solution has a very significant effect. And yeah, with too high electric conductivity, as you can see it here, it doesn't work for this electrochemical degradation. And now I want to give it over to Heico, who will present you the further results.
Yeah, thank you, Lara. Yeah, so we decided to continue with the lower conductivities. In this case, we had a synthetic drinking water with two different conductivities, one as soft drinking water and one for hard drinking water. And in this diagram, you see the fluorine mass fraction concentration in, and we also measured the fluoride. And the left part of the diagram, you see after 150 minutes, a decreased concentration of those carboxylic acids, and fluoride was produced as a product. And the balance, the mass balance of fluorine here is quite good. At the right part, this is the hard drinking water. You also see a decrease of the PFAS concentration, but not so much as in the soft drinking water, and you can't see fluoride. We think it was a precipitation of calcium fluoride. In the last weeks, we repeated this experiment. I had the chance to have a quick look at the results the last days, and I can say, yes, there is also fluorine measured after 150 minutes. So our idea, I think it's right, but I have to look closer to those fresh results. So the next slide. You see it's the same setup for the experiment with synthetic drinking water with spiked carboxylic and sulfonic acids with different pump rates. And it's only a slightly increase of degradation with 100% pump rate. And a little bit more fluoride is produced. It's around about 4,000 microgram with 40% pump rate and 4,600 at 100% pump rate. But we need a much more energy to produce the 100% pump rate, so we decided to continue with the 40% pump rate. So yes, there's a quite big amount of results here. Here we have done experiments with single substances. Those are all the carboxylic acids. The left with PFNA with C9, and on the right TFA. And you see all of those carboxylic acids were degraded in the first line. And in the middle line, you see the transformation products, the concentration of them, the molar concentration. And if you look closer to those gray squares, this is the TFA, which is produced as transformation product. And this is the one which is still in the end not totally degraded. But in the lower line, you see the results for the fluoride, and you see all of those degradation is made until the fluoride. Only when TFA is at last, it's not completely mineralized to carbon dioxide and fluoride, but mostly it is. So in the next slide, you see the results for the sulfonic acids. And the longer ones, they are degraded as well. You see also the fluoride in the lower line, which is builded. But the shorter the sulfonic acids are, yes, the lower is the degradation. And I think the TFMs never will be degraded at all. I've seen newer publications which show that electrochemical oxidation for sulfonic acids is quite better with another electrode material. but this we didn't have done by ourselves. Yeah, in the next slide you see the results with different current densities. Our idea was to make longer experiments with lower currents, but in the end we have the same current density. So we had here 500 milliampere and 720 minutes reaction time, but the degradation was not as good as when we worked shorter and with higher current densities. So we still continued in the most experiments with the 1.5 ampere. Yeah. And of course, we looked also for the byproduct formation. And yes, as expected, they are built. In this case, when we have chloride in the electrolyte, there is chlorate and perchlorate built. And if we investigated here different pump rates, but that doesn't make matter. Every time they were built. You have to have in mind this is a big issue in all of water treatment. All advanced oxidation processes will build them. So we thought about microbial degradation, which can degrade those chlorates and perchlorates, and also bromate, which is also a byproduct. Yeah. The next slide, there is one experiment with water from the pilot site 1, which is the so-called Rastatt site. And as you see, the carboxylic acids, which we spiked there, they are degraded also in those natural water, but the sulfonic acids, the TFMS is not degraded, and the PFB is only a little bit in this time. So I can give you a summary of all those results. Yes, the electrosorption and desorption from activated carbon produces concentrates, which are in principle treatable with electrochemical oxidation. And high electric conductivity will hinder the oxidation of the PFAS at the electrode. And when we looked for the pump rates, this didn't have a significant impact on the efficiency of the PFAS degradation. The longer the carboxylic and the sulfonic acids were, yes, they were transformed into the shorter ones first and then degraded to fluoride. But you have to have in mind always that transform the products were the shorter ones until it was degraded totally to fluoride. And also the head group was important for the degradation. Sulfonic acids were degraded much slower than carboxylic acids. With a higher current, we had a better mineralization. Even when we had the same current density, it was better to have a higher current at all. The byproduct formation we have looked for, and we think about microbial degradation. This we will do in a national project which is started already, and we look there for the microbial degradation. As well as we look to modify the activated carbon to have better properties of electrosorption and desorption. Now we have shown that in principle it's possible to have these effects, but they are too low to be considered at the moment for upscaling in waterworks. But the pilot plant from Condias is a ready-to-use system, where you can handle at the moment 20 liters. Condias is able to produce this also for bigger volumes, and it's working for these conditions we have shown you at the moment. So, yes, I think I'm finished. Thank you for listening, and we're glad to answer your questions.
0PM. Zero pollution of persistent and mobile substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under grant agreement number 101036756.